So, good evening everyone. Today is the 10th week of our course Microwave Remote Sensing in Hydrology. Today I'll be covering few of the topics like till now we have seen active microwave remote sensing. Now we will study about passive microwave remote sensing. What is passive microwave remote sensing? What are its advantages and disadvantages? And also I will discuss a quick recap to few more important topics, and also followed by one quick MCQ discussion. So first to know that we were studying about synthetic aperture radar, that is SAR, one of the systems in micro remote sensing. But before that it started with SLAR, that is the side looking airborne radar. So first it came that side looking, it was airborne radar, then SAR came. So what is SLAR? You can see this geometry here. It is again showing you the microwave region and how it is working, the microwave geometry of the signal, how it is taking the data, capturing the data, and this spectrum shows various of the from near to far range. So if our antenna is here, suppose it is our flight path, and this is our near range total swath, and this is the far range. This is the slanted signal going and the backscatter taking, and this is these are the swath. It shows that how this is taking the data acquisition, and here it is showing the graph about different land use land cover. You can see, so it is the return intensity, and you can see here the shadow area is shown, that is here. Suppose some height, it has some height, some of the targets, because our earth surface is undulated, it has varied target, depends on the targets and properties, many trees, hills. So here it is getting strong return, it says, that's why it picked. Then shadow area, there is no signal going back, and then some metallic bridge here it is. So the metallic bridge, it is getting very strong intensity return, then going down again, and here it is the specular target to return. Specular target, it gets some of the lands smooth surface, I mean not smooth, depends the course variation, but not with height, some land surface. Suppose it may be normal bare land or an agriculture field or water surface, any. Here I mean take it as water surface, because we can see it is almost like a canal going and the bridge over, and then some vegetation and some hills. So it shows varied targets, and how generally the return intensity, spectrum, profile going on. So if we see the radar image, it is one location. So we can see it is these are the features, various features present there. These are the ridge and valley and river going this way, and the bridge is there. Okay, there is the Tucker ridge and human ridges. So it will come in radar image, it will show like this. So ridge and valley, you have to understand, ridges are the peak line, top profiles, and valley are the in between. So how this is creating shadow here, one part, because these are in height. So when the loop direction, radar loop direction from this side to this side, from your right to left, as we saw in previous also. So because of that, the far range that side, the shadow is coming. So shadow means these has no signal region. We will not get any signal from these regions. And also these are the water body, the black, and we already studied that why water bodies come as darker in radar image, and this river is going in between like this. So this is one thing to read the radar image. So in real aperture radar, the image comes as this, and synthetic aperture radar comes as this. So real aperture radar, we already saw it is the aperture, the antenna length is real. We are not synthetically increasing the antenna length. It is how it is there. So by seeing, by looking at the images, that the real aperture radar image is much more of lower resolution or coarse in the image as compared to synthetic aperture radar image, and here it is of high resolution or very fine image, not that coarse, because here we synthetically increase the aperture length. That's how we increase the azimuth resolution also. So this is how we increased our image quality from real aperture radar image to synthetic aperture radar image. Now there it shows the different flight orientations for capturing images for SAR interferometric pair. So SAR interferometric pair, we already studied about the basics of INSAR. So there we already studied about this diagrams, and also you can see here that pair we need for that interferometric processing pair of images, at least one pair of images. So there it can be from opposite direction, opposite side configuration, and also for same side configuration. So in both way the image will be different, slightly different. In what way? Different in, you can see for the first scenario when it is in opposite side both, the shadow are not that much, the appearance of the shadow are not that much as compared to the same side, because here it is when the loop direction are opposite, it is cancelling few of the shadows, because from this side when it is looking, okay, this portion it gets shadowed, this portion, and together it can mitigate some of the shadows. But when both are same side, both are looking from the same side, so both are getting shadow at the same parts of our target, so it can't mitigate that much shadow. So here you can see these are the more shadow as compared to these are brighter, at least some signal it is getting from that part. So by flying the radar along parallel flight lines such that illumination always comes from same direction and appropriate incidence angles are maintained, strips of images can be acquired with identical shading characteristics, which allows these to be merged into mosaics. That's what I said, that from the pair we are creating a mosaic, ultimately one image from two of the data. So in the mosaic, finally what we are getting, the image is a composite of radar strips taken during a flight series over an uneven hilly terrain, making up part of an ingenious or metamorphic silt in Nigeria, in Africa. This mosaic is about 97 km on a side. Even though the surface is heavily vegetated, with tropical forests, penetrating radar shows mainly its topographic character, particularly identifying fracture systems that have been weathered out into narrow valleys. So you can see here the terrain profile, but actually what it says that it has tropical forest cover, but as per the data, the band we take to image this for this particular, that can penetrate this portion. It is not C band, definitely it can be X band or L band. Mostly it is X band image, so it can penetrate very easily. No, not X band. X band is very lower in wavelength. L band or P band it can be. So that has higher wavelength. So higher wavelength can penetrate through the forest and can see the terrain. So here we are getting the terrain profile. And topographic character, that is how it depends on what we want to look. We want to look below the forest or above the forest. Another image also showing some some magma of flowing, and it is mainly different of the application. Now we can see the SLAR, side looking airborne radar. So in above it is one SLAR image. River surfaces, roads and streets being smooth and flat, that is the dark. Buildings being strong corner reflectors tend to be bright. And most moist and bare fields, there is various darker shades, but those with crops have lighter tones. Brighter slopes are oriented towards the aircraft located around bottom of image. As the look angle increase towards top, a general darkening going to, that is this portion you can see there is the darker, and as you proceed to the lower image part of the image, it is brighter. So overall drop in signature. So this is because the look angle increase. Now one quick recap about the radar polarization. Some ground features appear about the same in either parallel or cross polarized images, that is the HV or VH. Vegetation tends to show different degrees of image brightness in HV or VH modes owing to depolarization by multiple reflecting branches and leaves. Other factors contributing to brightness or intensity of return signal, that is the polarization depends on these factors also of the target. These are the target characteristics. So dielectric constant, first, it is a dimensionless number determined as the ratio of capacitance of a material to that of a vacuum, relates to a material's capability to hold a charge. So basically when we are dealing with the electromagnetic signal, it is the radar signal, it is nothing but electromagnetic signal, and it is one type of energy. So it is energy, or you can in normal term, generic term, you can say charge. So it is all about how it is dealing with the energy, the targets, various targets. So it is the finally dielectric constant. It by lower or higher, it says that how much the material's capability to hold the energy in it. So higher it is more. It can hold the charge more. Radar waves penetrate deeper into materials with low dielectric constants and reflect more efficiently from those with high constants. So values for K, that is the dielectric constant, range from 3 to 16 for most dry rocks and soils up to 80 for water with impurities. Moist soils have values typically between 30 and 60. Variation in intensities of reflected pulses may indicate differences in soil moisture. So these are these are not the absolute values. These depends on your study area, site to site. But here one example, at least some range it shows that okay, the the dielectric constant value for dry rocks and dry soil, it is not that much. It is obviously not 50, 60, 80. It varies between 3 to 16. And for water, we all know it is the highest, that is 80. And also it is not all water. Water means there are various types of water. Here normally it says that water with impurities, that is normal. And moist soils, that is these ranges are useful because as we are studying that this course is about the hydrology that deals with dealing with the flood detection and also soil moisture, water bodies, all these, every type, every domain related to water. So one very popular application of radar microwaves in that is the soil moisture estimation. And for that this particular characteristics is very useful. So here it says that moist soils have values typically between 30 and 60. That also varies, but normally it is from higher side. So moist soils, so dry soil and moist soil. So that is how we can differentiate between dry soil and moist soils also. And that because of that, variation in intensities of reflected pulses may indicate differences in soil moisture. Now second is roughness. So roughness refers to irregularities of dimensions that relate either to texture of the surfaces or of objects on them. So the height of an irregularity together with radar wavelength and grazing angle at point of contact determines the behavior of a surface as smooth, that is the specular reflector, intermediate or rough, that is the diffuse reflector. So another property is roughness, the irregularity of dimension that relate either to texture of the surface or of objects on them. So here an example showed the images for two different polarization, one cross polarized HV image, another HH image. So you can see in HV image what to look at for HH and HV. In HV image, the targets with height are sensitive to the HV signal, this HV polarization. How to look at that? That you can say the relief or the profile, it looks, it appears as with height here all over as compared to HH. So HH is more sensitive to the surface, flat surface, you can see, not that don't have height. So what to conclude from this? So HH can be useful for flood or water smooth surface that obviously does not have height, but when you are interested to detect suppose buildings or some trees, hills, all those, you want to look at those features, then HV is important. So both has different sensitivity of the target. Here also it shows. the same HH and HB and HH. Now radar penetration. This is the another capability of radar signal. So radar wavelength influences penetrability below target tops to ground surface. So what to penetrate? Target top to ground surface. It is not like going below the ground. So depth of penetration increases with lambda, that is wavelength. So L and P band radar penetrates deeper than K or X bands, definitely, because L and P band have higher wavelengths. Shorter wavelengths such as C band reflect largely from forest canopy tops. At longer wavelengths, tree leaves are too small to have much influence on backscatter, although branches will interact so that canopies are penetrated to varying degrees. Survey image shows L-band radar has penetration through the dense, continuous tropical vegetation cover of the Amazon basin in Brazil to image the gently rolling terrain beneath. So you can see the Survey L-band image and penetration through the dense, continuous tropical vegetation cover the Amazon basin, and it shows the terrain below. Similarly, CSAT radar can also be co-registered with Landsat imagery, that is the optical Landsat satellite. Part of a Landsat image of dissected Allegheny Plateau in West Virginia, seen alone in the upper right, is here superimposed on a CSAT image, giving a new impression of apparent relief by virtue of the light tones in the certain foreslopes. So image fusion. Here comes the another aspect or another branch of the application. You can, the microwave remote sensing, it has its own advantages, disadvantages also. Similarly, the Landsat or optical data also has its own advantage and disadvantages. So you can get the advantages if you have data. Suppose if you have meaningful data during, suppose, a flood time, then you want, if you get the data of no cloud for the optical image, then you can fuse the both image and get the characteristics or the information from both the data. So it will definitely improve your work. Again, the SAR, that is the subtle imaging radar, utilized an L-band SAR HH band system capable of 40-meter resolution. So near to far range depression angles for this fixed loop radar fall at 43 to 37 degrees respectively. So drop in angle diminishes foreshortening and layover effects. In this part of area consists of strongly folded some rocks and organic granite cores. Now geology is displayed as the basalt and volcano. These are the volcanoes. So collapse is triggered by the emptying of the magma chamber beneath the volcano, usually as the result of large volcanic eruption. If enough magma is erupted, the emptied chamber will not be able to support the weight of the volcanic edifice. How the eruption comes? These ring fractures serve as feeders or fault intrusions, which are also known as ring dikes. Secondary volcanic veins may form above the ring fracture. So it can image all these things of a volcano. So whoever studying the volcanoes, its geology, its rupture and all those, then there it's very useful also. Again, volcanic, the calders and the another thing to see. So dendritic drainage. So you can see the patterns. It is called the dendritic form, captured from the survey image of East Central Colombia, results from uplands covered with grass that, because of the blades are small, strongly reflects away the radar beam. Thus appears as darker, whereas the streams stand out as bright because their tree-lined channels produce double bounce reflections between the smooth water and tree trunks. So very important to understand this or notice that what we see normally streams, in the sense these are the drainage, these are the waters, okay, water profiles, but here it comes as bright. But what we see that in radar image, in microwave image, these water, any water, this body and rivers comes as darker, very dark, not at least this bright. So why it is coming as here bright? Because that here the streams, here the outside by all are the trees covered with grass, upland covered with grass. Grass are very pointed upward kind of feature. So the streams stand out as bright because the tree, side by there is tree to the ground, suppose the water body, it is resulting a double bounce effect here. It is not resulting thus specular or reflection. Okay, so double bounce reflection, that is how it appears more in energy. Now the signal is not reflecting away the antenna, it is reflecting towards the antenna, and also because of the water has higher dielectric properties, and also the double bounce is happening here, so it is going to the antenna, reflected back to the antenna with more energy also. So this profile appears as brighter here. Okay. Now a Lancet sub-image of the desert with northwestern Sudan, because dry sand has a low dielectric constant. Now to understand, dry sand obviously doesn't contain water. Radar waves can penetrate the small particles to depth of several meters, about 10 feet or more. Okay. The inset radar strip trending northwest actually images bedrock at the general depth below the loose alluvial sand and gravel, which acts as though almost invisible. So a channel subsurface topography is revealed with valleys correlative to specularly reflecting surfaces and uplands shown as brighter. So here what we see, all these totally the color image is a Landsat, but this strip is showing one radar image. Okay, radar image with suppose higher wavelength. So here it is, and it is very dry sand. Here it is penetrating the dry sand. Okay, the small particles also, the loose particles, to depths about 10 feet, up to 10 feet it can penetrate, and by penetrating it can show the subsurface, the below the ground. And for studies, various studies, application of the desert or drought, you can say drought area, we are seeing flood also, but we have to understand the drought also sometimes. That way this area, we can why that is happening, how that is happening, we for study you can see the below the ground, below the the subsurface of the topography is revealed with valleys correlative to specularly reflecting surfaces and upland shown as brighter. So these are the valleys, the darker portion. Valleys means it is suppose the lower in height. So that is coming as darker, and the upward, that at the at least some level, not to ground but below the ground, that is coming, I mean ground to more in the depth. So more in the depth are darker. So it has this profile. You can see here, these are from the Landsat image optical. You can't say this anything, but here this profile you can see below the or beneath the surface. And this is very useful in drought region also, drought season, drought region. Now, SAR-B satellite has a variable look angle that ranges between 15 and 55 degrees. SAR-C has L and C band radars, each capable of HH, HV, VV and VH polarization, and X band instrument in VB mode. All had variable look angles that image sidewards between 20 and 65 degrees, producing resolutions between 10 and 25 meters. Advantage of this multiple system is ability to combine different bands and polarization into color composites. Set of images showing the volcano, these in SAR-C in 3 polarization modes. Okay, just showing in 3 polarization modes. So multi-band, multi-frequency image of San Francisco is very famous. San Francisco Bay Area. Says this is the coastal is from L band, where HH is red, HV is green, and C band, where HB is blue. One of the most pleasing to the eye and a prime example of why so many people are to live in the Bay Area. So this is one standard image to understand multiple and multi-frequency data. Another thing to see, the Nile River. So this image is the space shuttle color. This is the infrared photograph, infrared signal, and this is the SAR-C, the microwave signal. And here we projected or we created one composite image where red is from C band HV, green and blue from green is from L band HV, blue from L band HH. So from multi-band and multi-frequency, why multi-band, C band and L band, and also frequency because it both has different frequency and also does different wavelength. And for visual purpose, we can see these are coming. So L band is 6 cm average, and C band and L band at 24 cm. So this is coming like that. The image. These are the oil fields, wells, you can see. So how different targets appear differently. Now see radar imagery taken on 2 dates or with 2 antennas can be processed using interferometric techniques that use signal phase difference to determine differences in distance to point targets to yield information on topographic variations. When combined with digital elevation model data, single pass or color composite radar images can be shown in perspective views as anaclips recurring, that is the stereo color glass, or even in simulated flyby video movies. A perspective view of Death Valley and Anderson Mountains made from SAR-C imagery is a good example. So basically what we can get from that basically says that from one pair of image, okay, and what we are getting that we studied in interferometry basics, that we were calculating the phase difference of the pairs and also not only with the difference of pairs, also for different dates also. If we calculate that, then obviously we can detect some change also between the dates, and that is how we can monitor the land or the target of our interest, and that way we are getting some height. So when combined with digital illusion model, single band or color compared array can be shown in perspective views, and that is how we can create this type of images, okay, for using the 3 image. So one quick recap, the radar equation we already saw. This is the reflected power, WR is equal to WT, transmitted power, G is equal to gain, lambda wavelength, sigma is the backscatter area, effective backscatter area, by 4 pi cube r to the power 4. R is the range, distance from transmitter to target, the range detection R. And in this equation, it is very difficult to measure the parameter effective backscatter area. This can be simplified by replacing the same by the multiplication of scattering coefficient and ground resolution cell. So here we simplified the equation and we got, this is the scattering coefficient into A, where A is the ground resolution cell. So basically, to understand the numerical equation, this is the power received is equal to power per unit area target, okay, into effective scattering area of the target into spreading loss of radiated signal into effective received area of antenna. These are 4 of the components we are dealing with from this equation. So this equation we can get this is the meaning. So radar backscatter coefficient is the efficiency of the terrain to reflect the radar pulse, is termed as the radar cross section. The radar cross section per unit area A is called the radar backscatter coefficient and is computed as the sigma naught, that is equal to sigma by A. Okay. The radar backscatter coefficient sigma naught determines the percentage of electromagnetic energy reflected from the from the ground back to the radar antenna, and we are calculating as backscatter sigma naught. We saw gamma naught, sigma naught, so this is the sigma naught and we are calculating this. So the ground resolution is again dependent on the slant range distance of the target and pulse duration, which can be understood from the following equation, is equal to effective beamwidth beta into R, that is the range distance, by C tau by 2 cos gamma. C is the velocity of electromagnetic radiation, that is the velocity of light, and tau is the pulse duration, by 2 cos gamma is the angle of incidence. So these are the standard notation actually. Effective beamwidth beta, normally we don't use the h, small h, only beta. R is the range, C tau is pulse duration, by 2 cos gamma is angle of incidence. So what it is giving? It is giving the ground resolution A, okay, that we are interested in the image. Finally, from the radar signal we are creating some image, so we need this resolution, and how to improve the resolution also. So this till now, this was a quick recap to understand the passive micro remote sensing. Till now we have studied the active micro remote sensing, that because it deals with it is captured with the active sensor. Active sensor means it is operating on its own energy. Because of that, it is very heavy, very costly. It comes, and all the missions are very active missions, active sensors missions are very costly also. But there is passive micro remote sensing also. So what is that, and what are the advantages and disadvantages, what are the various uses, we will see. So although active micro systems, that is radar, are the more commonly used sensors for this region of the spectrum, passive microwave sensors also have provided information about the Earth's surface, its oceans and its atmosphere. Air and spaceborne passive sensors have operated for several decades. They measure directly radiation incited by thermal states in this media and hence are representative of natural phenomena inherent to the materials as passive. So passive microwave region is from 1 to 200 gigahertz, better to understand 0.15 to 30 centimeter. The principle underlying passive microradiation is implicit in the above spectral curves that show relative intensities of radiation or radiance as a function of wavelength for materials with different intrinsic characteristics. So here it shows the UV visible in the electromagnetic radiation total spectrum, and there this wavelength, I mean, it is showing the sun energy, the molten lava, forest fire, and like this. So these are the response, the wavelength in centimeter, and the intensity it is getting, the sensitivity to intensity. So you can see for visible the sun, it is the maximum, and it increase from, I mean, the lower to higher, then wavelength is that. So at this wavelength it is the highest. Similarly for forest fire, the near infrared is highest, and the middle infrared and all is far infrared. So there is radiation from natural bodies at low temperature, even at longer wavelengths, right part of the curves and beyond, that extend into the microwave region. This radiation, which is emissive, is generally much weaker in intensity compared with shorter wavelength outputs, but it is detectable by sensitive instruments and also is not much attenuated by the atmosphere. The temperature measured by these instruments are brightness temperatures. In this family of curves, land, water, air and ice have different brightness temperatures, and thus we can separate them in many cases and sometimes uniquely identify them. So there is another, different way to read these images and to understand. So the wavelength segment employed in passive micro remote sensing is generally between 0.15 to 30 centimeter. Most commonly used frequency centers are the one for thus the multispectral mode. But the signal beamwidth is usually wide in order to gather sufficient amount of the weak radiation. So the spatial resolution of the instrument also tends to be low. So in passive micro remote sensing, we don't get that high resolution like active micro remote sensing. So commonly in kilometers from space and in meter from aircraft mounted sensors. Allow the sensor to work with large sampling areas that provide enough radiation for ready detection. The sensors are typically radiometers that require large collection antennas, fixed or movable. So microwave radiometers, advanced microwave sounding unit that started in 1978 till present, scanning multi-channel microradiometer, spatial sensor microwave imager, tropical rainfall measuring mission TRMM, that is very useful, the most useful in our domain in hydrology, TRMM, advanced microwave scanning radiometer AMSRE. So TRMM from 1997 to present, it is the mission, and we can get the rainfall data from this TRMM. So passive microradiometry, passive microwave sensors using antenna or horn to detect photons at microwave frequency, which are then converted to voltage in a circuit. So scanning microwave radiometers, mechanical rotation of mirror focuses microwave energy onto horns. So comparative characteristics of few of the sensors passive. The first one is Nimbus. It is more known to the Nimbus sensor, and second is the SSM one, and also Aqua, the third one. So these are the time period for it ran, it ended, and it is still running, and the Aqua mission. These are the more known common term of these, that Nimbus, Aqua, SSM. Frequencies, different frequencies it can operate, and sample footprint size. Okay, when this is in 6.6 GHz, it is the footprints, and these all are in kilometers, 27 by 10 kilometer and 17. So one thing to understand, if you remember, for the active micro remote sensing, that to 1 swath at least, it was not covering this much area. Here when this is in kilometers, so it is covering so bigger area, larger area. So when passive studied the passive micro remote sensing, this is the very important. So microwave brightness temperature, microwave radiometers, using radiometers what we measure, can measure the emitted spectral radiance received. So this is called the brightness temperature. If you recall your optical remote sensing knowledge, these are the similar to that. There also we study the brightness temperature, the spectral curves, those. So and is received is linearly related to the kinetic temperature of the surface. The Rayleigh-Jeans approximation provides a simple linear relationship between measured spectral radiance, temperature, and emissivity. So for optical we use the spectroradiometer. Here we are using the microwave radiometer. So similar. Again, the sensitivity to different the related energy at long wavelengths, more you go to right side, such as in the microwave region, the relationship between spectral emittance and wavelength can be approximated by a straight line. So this is the line it is showing. Okay, so this is the visible portion. Then further, so for different liquid air, dry ice, red objects, and finally the sun, as we saw in the previous one graph also, if we connect the peak, this maximum sensitivity lines, and you can see it is the approximated one, the straight line. So as we proceed with the wavelength increasing, it is like this. So this portion we are getting. So what is the Rayleigh approximation? So the spectral the radiance is a linear function of the kinetic temperature, the T. K obviously the Planck's constant, C is the speed of light, is the emissivity, T kinetic temperature. This approximation only holds for when lambda is very greater than lambda max. So what does it mean? So when the lambda is the sensor lambda, I mean the signal lambda, and this lambda max is our target, the lambda. So it is only useful when it is that, as compared to our target, it is that much bigger. Okay. So finally, the brightness temperature, it is T B, we can get from here, and here you can see it is, it depends or proportional to lambda to the power 4. And brightness temperature can be added to kinetic temperature through emissivity. Because emissivity also another character of the target, as we saw for the polarization, there the dielectric constant, one character characteristics of a target. So emissivity another also. So thus passive microwave brightness temperatures can be used to monitor temperature as well as properties related to emissivity. So it is reading, as I said, that active microwave sensing, that data we learn how to study. For passive it is similar, because but different. You have to learn how to study this one, because here the acquisition is different, and so the parameters we are reading is different. So on land, passive microwave surveys are particularly effective for detecting soil moisture and temperature, okay, because of sensitivity to water. Microwave radiation from below thin soil cover is contributed by near surface bedrock geology, and assessing snow melt condition is another use. Tracking sea ice distribution and condition is a prime oceanographic application. Another marine use is for assessing sea surface temperature. That is the most popular use of the passive micro-remote sensing, sea surface temperature, because it is sensitive to emissivity. Okay. Passive microwave sensors are important components on some meteorological satellites, being well suited to obtain temperature profiles through the atmosphere, as well as water vapor and ozone distributions and precipitation conditions. The ESMR, that is the electronically scanned microradiometer, and SMMR, scanning multi-channel microradiometers. These are the different instruments. Scanning microwave radiometers flown on Nimbus medstats are very useful. Here is an ESMR single band, that is the frequency with this image received from the Nimbus set provides sea ice data for both polar regions, the Antarctica. So open water appears in grey-green tone. So these are the, so one thing to understand, that it can take data for very larger area, the acquisition. So when you want to look at very larger portions of the whole of the polar this region, then it is so useful, and also because of its sensitivity to, like obviously radar, this region, so there it is useful. When you don't need that high resolution, coarse resolution can work. Several other satellites, that is the TRMM, as I said, for our domain it is the most important, use passive microwave to learn more about meteorological conditions. So one of particular versatility is the SSN, that is special sensor microwave or imager on the US satellites. It can measure such variables as wind velocity, soil moisture and rainfall. One of its prime function, useful for both military and civilian needs, is to monitor sea ice, much in the manner of the SMR. Here is a SSM derived map of polar ice in the Arctic region, with the left panel showing winter distribution and right in summer. Currently so many research going on because of the glacier monitoring, glaciology and all this, using the radar remote sensing. Now radar remote sensing, they can use the active, they can use the passive. So here the passive one is more useful because it is not that costly like active in terms of data acquisition. Because for active remote sensing, to see this larger image and also this to get this type of data, all those, it is definitely, it will be commercial, so that is very costly also in time. So it is useful, and also to cover, to get this much of swath area. Several of its channels to determine brightness, temperature over land and sea. So this image shows variation of such temperature of the water of the Gulf of Mexico. As I said, the sea surface temperature. Sea surface temperature is directly related to, if you can see, I mean, if you say that no, it is not in our domain, but sea surface temperature is in our domain. In our domain means if you are dealing with the flood and disasters related to hydrology, because all those disasters or any cyclone, typhoon, all these things relate to the sea, and the phenomena, the sea surface temperature phenomena, it creates that type of natural disasters. And because of that, so when you are into monitoring, or you are into suppose not into flood detection but early warning system, this type of early warning system for suppose flood, so then you need this type of data, this type of information, that what is happening in sea surface, the temperature, the change and the variation, and that is directly related to any, if any phenomena is forming on the sea, it can detect, and based on that you can tell that okay, I mean some disaster is coming, some this kind of, and this kind of clouds also that contains this much of data, vapor, all those. So this is another domain. So the application, passive microwave application, definitely soil moisture, snow water equivalent, sea or lake ice extent, concentration and type, sea surface temperature, atmospheric water vapor, surface wind speed, cloud, liquid water, rainfall rate. Monitoring temperatures with passive microwave. So sea surface temperature show the over the larger area, surface temperature blue to red, the scale, land surface temperature also, like this. These data are mostly available open source, so most of the times it is one additional data, as in one additional data you can use. Okay. And mostly useful for data analysis for any task, and mainly for early warning system, the sea surface temperature. So passive microwave sensing of land surface emissivity difference. Now coming to land. So microwave emissivity is a function of the dielectric constant. Again, it is emissivity, and obviously it relates to dielectric constant. Most earth materials have a dielectric constant in the range of 1 to 4, and dielectric constant of liquid water is 80. We already studied the first part today. Thus moisture content affects brightness, temperature. Surface roughness also influences emissivity. So the similar but not the same, the brightness, temperature here. Soil with dry snow and soil with wet snow. So here the white circles are saturated with water. Okay, these are the particles, water particles saturated with water. And two understand more this image, here you can see the in between spaces, and here it is a little bit wrong representation. Better to say when it gets wet snow, in between this particle of the water, it is there comes the water, and this is the bare soil. So what happens, how it is related? So snow water equivalent, as the water reduces, the highest, because the dielectric constant is so high for water, when it gets the water, gets higher in brightness, to understand that, and it reduces or decreases like as we go on in decreasing the water content. So snow water equivalent, this is the snow water equivalent in millimeter. So snow to water, how much snow? As I said, it is very important, and recent studies are going on for snow monitoring and this monitoring of the Arctic region, because we are the global warming and glacial melt. So this kind of images we can get, or data we can get from SSM, Northern Hemisphere snow water equivalent, millimeter of water. So you can see these are the snow till and the water, and here it is okay. But if we, studies are going on that different season change. So looking at the change, suppose in winter season you get the data, and in summer or later season you get the data, then you can see the change and you can see the variation. This kind of researches are going on by agencies, that there they are identifying that how much it is deviating, how much the glacier is melting. Snow season, obviously there will be much more snow, but then in the summer season there will be lesser snow, but how much less, how much it is changing, for that these are useful. Now atmospheric effects, this is one important aspect of the passive microremote sensing. At frequencies less than 50 GHz, there is little effect of clouds and fog on brightness temperature. That is, it sees through the clouds. That's simple to similar to the active sensor. Thus, passive microwave can be used to monitor the land surface under cloudy conditions. In atmospheric absorption bands, passive microwave used to map water vapor, rain rates, and clouds. So, why it is used? Because it is more sensitive to the water vapor and clouds as compared to active sensor. Okay, so you can get some data, the atmosphere. So mapping global water vapor. So as I said, for the early warning system, suppose sea surface temperature is one phenomena to look at, and the global water vapor, that is the cloud that contains the water on those. So looking at that, studying the data, and along with the sea surface temperature, you can people are doing research on that domain, that if any the cyclone or this or rain fall is coming or not, looking at that. So that way it is, and also depends on the historic data. It needs historic data, many historic data, because it needs the pattern or the data pattern to conclude that okay, this region, when it ranges from this, we should get prepared of flood like situation. So that is how the early warning system. We are not detecting flood here, we are saying that flood will happen, flood may happen, so be prepared, and that is much more useful and in demand compared to flood detection. Flood detection in disaster mitigation, there is the response, there is the recovery, many parts is there. Okay, so when the before the disaster, get prepared, and after the disaster, the recovery. So every domain has its specific use. So here the early warning system is the most useful, because after everything we should reduce our cost, our damage. So for that we can't stop, or there is one very important saying in disaster studies, that you can't stop the what is coming, any cyclone or this rainfall, but you have to get prepared. You can get prepared, better prepared for that. So for that purpose, these early warning systems are useful. So passive microwave sensing of rain over the ocean. So microwave emissivity of rain or liquid water is about 0.9, and emissivity of the ocean is much lower, 0.5. So changes in emissivity are seen by the measured brightness temperature, provide the estimation of surface rain rate. Okay. Now over the land surface, so microwave scattering by frozen hydrometers is used as a measure of rain rate. So physical or empirical models relate the scattering signature to surface rain rate. So this is the physical and empirical model. These contain your historic data, other cases data, and that case is based on those data information of suppose last 100 years data, that it says okay, these ranges the rain rate, and these ranges these. That way it is used. It relates to the scattering signature to surface rain rates. Hydrometers. So rainfall from passive microwave sensors, accumulated precipitation from the TRMM. So TRMM data are very useful, and we can see from this that accumulated precipitation, it is most likely to rain and all those. Now one advantage and disadvantage. We will discuss this more in our MCQ session, but here to understand first that the advantage of passive microwave remote sensing, it penetration through non-penetrating clouds, and radiance is linearly related to temperature, that is the retrieval is linear, and highly stable instrument calibration, that is very important. We are using the radiometers for passive. The calibration, the control is much higher as compared to active sensors. Okay. Global coverage and wide swath. This is also one of the most important advantages, that it has very high coverage. And disadvantage, larger field of views compared to visible or infrared sensors, and variable emissivity over land, and polar orbiting satellites provide discontinuous temporal coverage at low latitude, need to create weakly composition. So this is another aspect, that it needs more continuous acquisition, because polar region is much more important now to monitor, but now it has discontinuous temporal coverage at lower latitudes. So comparison of satellite stars and aircraft stars. So satellite star, we already saw that airborne radar and the satellite, the radar. So advantage of satellite SARs are more coverage per second. Obviously, using an aircraft you can't get that much coverage. Lower operating costs, not constrained by flying conditions or airport proximity. Wider area views, and somewhat simple signal processing, no motion compensation. So this means as compared to aircraft, first is more coverage. Aircraft does not get that much angle because it is flying in lower height as compared to satellites. Lower operating cost satellites have, because an aircraft, it should be one, one pilot, and also other the flying and all the mission. It is not controlled or automatic, it cannot be. So somehow how the operating cost increase, not constrained by flying condition or airport proximity. Obviously when you are flying, suppose take the drone or UAV as example. If you want to fly UAV, you have to take permission. You can't fly UAV over the military area and over a city just like that, over administrative buildings. Everywhere you have to take the permission. But when flying the satellites, it does not need those type of permission or the airport proximity. Obviously it is the satellite, it operates in the very higher part of the our space. So the where the flights those are operating, it will not interfere that portion. Wider area views, definitely, and somewhat simple signal processing, no motion compensation, because this is very important. Because thus when you are suppose the satellites, it is very pre controlled or pre, what to say, it is programmed before. It is not like real time controlling. It is programmed before and it is not shifting that way. But for airborne or for suppose this drone type, this thing, it has the motion compensation. It is it has the interference of very way, the wind and all those. So there is the motion, the motion compensation. It is in the motion, so to correct or various error due to the motion. So that is simpler in satellite but difficult in aircraft. Now disadvantage, more expensive to design, build and launch. Definitely satellites, it is much more expensive to design and build and launch. More difficult to provide multiple polarization and frequencies, obviously very much costly. Cannot be flown anywhere on demand. Yes. And lower resolution in ground, that is the another. So you have to understand, you need high resolution or you need more area coverage. So for high resolution, go for the active sensor. For more area coverage, go for the passive. And also the multiple polarization and frequencies. Satellites are that have multiple polarization, more than 2. Those are not open source because those are so costly, you have to buy data. But aircraft data, those are better to, because it is acquiring the data in much more smaller quantity. comparison of imaging geometries. The space bone, as I said, it is looking from very up height, so it can see a lot of the part, that is 25 to 500 kilometers, and airborne SAR, it can only 10 to 100 kilometers. Choice of swath width, so limited by range ambiguities and data handling capacity. A trade-off between azimuth resolution, number of looks, processing capability. So for satellites it is 30 to 150 km typical, and for aircraft 10 to 100 km. Radar set gets large swath width per beam by reducing the resolution and using careful antenna weighting to control range ambiguities. And radar set and UV is scan set to get extra word swath. So different mode are there. The scanner, the strip map, all those are different mode. In scanner you get the very lower resolution but very higher coverage of area. Here set 1, it was a mission, it ended. Imaging modes of radar set 1, so fine, standard, wide and scanner. Scanner ranges in kilometers. This is one. Various imaging modes, the comparison. Okay, scanner narrow, scanner wide. You can see the red part, how bigger wider coverage it can get. The fine one, the wide, the standard. These are the comparative. Beam modes and resolution, similar thing, fine, standard, wide. For radar set, that is the satellite based, and this is the resolution. If you can see, fine it is giving you 8 meter. For scanner wide, it is giving you 100 meter. So the resolution and the area coverage is, you can see here 50 by 50 kilometers, and here it is 500 by 500 kilometers. And country specific, it has the coverage, can provide complete global coverage with the flexibility to support specific requirements. The satellites ground track is repeated every 24 days. It has the temporal resolution 24 days. Radar set can provide daily coverage of the Arctic, view any part of Canada within 3 days and achieve complete coverage at equatorial latitude every 6 days using 500 km. So because of that, repeat pass, because of this repeat pass, it can see, look at one, suppose you are interested in one position here, then it can look, it is passing here this way, and every 6 days equatorial latitude nearby equator every 6 days using a 500 km wide swath. Look direction, so right looking sensor facing east during ascending, facing west during descending, and controls the orientation of the radar beams with respect to the surface structure alignment, ascending, descending. So these are the important thing to understand, because suppose you are interested to get data before the flood and after the flood, but you have to check for different sensors and what you are getting. And after the flood means, suppose flood happened on the date and then after 6 days you are getting the before and after, so that is not useful. So more the frequent better, but it also depends on when it is passing. So the look direction, it obviously it changes. Look direction comparison. So find beam position 2. This is the ascending pass and descending pass. So how the appearance you can see changes. And one thing to say that it should not, you should not deal with or work with different paths or different loop direction. That means if you are getting or acquiring one ascending pass before the flood, you should get ascending pass after the flood, because these two, the intensity of the backscatter changes. You can see here it is, say it is getting some profile, here it is not, because it is in the different loop direction. So if you can't compare these two, because these two are looking at the ground differently. Okay, if you want to compare, you have to take same as either ascending same or either descending same, the pair. Otherwise the intensity and all those will change. It will give you wrong result. Radar set 1, these are different. You can get from the sample guidebook the angles on. Also came. This is also one of the major how it started, the ship detection, and that also started because of the military purpose, detection of the vehicles and detection of ship. This is the ScanSys strip, and you can see the data, I mean the white coverage it is getting. Antarctic mapping mission, very important mission it was. Now RASA 2 came, it also has this. I am not going into that detail. It is limited by range, ambiguity and data handling capacity. Left and right looking antenna, similar. Now it has the imaging mode, it adds too much ultra fine wide and narrow. Normally you will get ultra fine. So before it was standard wide fine scanner, and now the ultra fine also added. Now the subtle radar topographic mission, SRTM. So that gives us the open source digital elevation model. That is the mission, and by that mission prepared the globally the DM, and it is prepared as I discussed before by this different loop direction, and how we are getting the height. The SRTM, it is the antenna or auxiliary, the radar, the array of the antenna, 60 meter long space shuttle. So it obtained ascertain the elevation data on the near global scale to generate the most complete high resolution digital topographic database of Earth. SRTM consisted of a specially modified radar system that flew on board the space shuttle Endeavour during an 11-day mission in February 2000. So there is these two types of antenna panels, C-band and X-band. The near global are made from the C-band radar data, and data from the X-band radar are used to create slightly higher resolution DM, but without the global coverage, that is the S-band DM. But normally what we use the 30 meter resolution SRTM data, that is the C-band DM with a 90 meter resolution can be downloaded free of charge on the internet, and 30 meter resolution also for, and we get 30 meter resolution for all over that is resampled from 90 to 30. The availability, of different topographic maps they scale, because the topographic maps and the different scales are available. So, although topographic contours supply fairly accurate information about elevation and slope being derived from an interpolation between precisely determined reference points, the elevation is always estimated and stated to the nearest meter. The need for generalization in topographic maps results in a loss of detail and accuracy. So modern instruments like electronic theodolites and satellite, the GPS receivers, provide point measurements, and generating terrain maps is a time consuming and costly process. So aerial and space-bound stereoscopic images produce wide area coverage using photogrammetric principles. So SRTM, why SRTM? So the homogeneity, the SRTM DM is the first continuous large-scale product that has not been mosaicked from data derived from different sensors, formats and dates. Resolution improvement compared to the only existing global DM 1 km horizontal resolution, this is the USGS available. SRTM DMs at 90 meter resolution with a relative vertical accuracy of less than 10 meter offers a great improvement. So evaluation coverage, this SRTM data is not classified data in C-band, covers nearly 80% of the Earth's surface, and 90 meter resolution basically for free, can be downloaded. So the resolution of 30 meter data, the mission system day and night on those. The interferometry already studied. Here it is coming because how it made the DM, the getting the height, because of in interferometry we get the phase difference, and from the phase difference we are getting the height. I am not going into this INSAR because coherence is important to our data, to our domain, hydrology and flood, but not INSAR. Just to get some idea, that is enough. So this is the phase, source and amplitude. So it is interferometric phase. It is certain elevation products different. The error also. So problems on SRTM use are black areas at data voids due to shadowing. Definitely shadow will be one entity in that will be in radar because it is side looking, and due to shadowing, phase unwrapping anomalies, all those can come. And in INSAR studies, the shadow is very difficult one to handle. And how we deal the shadow in any domain, in suppose flood detection or any hydrological application or any for DM also, we interpolate. Interpolate means based on the side by area we interpolate, and because shadow means no signal, and when there is no signal we can't do anything, and when there is no signal we better to interpolate from nearby based on various conditions, based on our, because in suppose hydrological application in flood detection, how we interpolate the shadowed region, we interpolate like suppose it is we see the proximity first, the proximity to river, proximity to any nearby flood pixel presence, all those. So based on the distance, and there are the many proximity analysis. Based on those, we fill the the no signal pixels or the shadowed pixels. That is very important in flood detection. We have to interpolate, otherwise there will be data gap or information gap. So DM optimization, no need to all those. DM modification. So original DM and it is processed. What we are using, that is the processed DM, and after many corrections, additional parameters, drainage net overturn index, all those. So finally we studied about the radar remote sensing, and we saw a quick recap about the active radar remote sensing, and followed by the passive micro remote sensing, and then we saw the SRTM, that is the product of the interferometric phase. Now based on today's topic, I prepared to discuss one MCQ session. Yeah, if you want, it is always better to submit, to mail me that MCQ. It is not mandatory, it is up to your interest, but MCQs, that is why I prepared the MCQs, that is in MCQ form, because I don't want any submission. I want you to get involved into the discussion to better understand the topics. So few of the questions I will discuss related to today's topic. So which of the following correctly describes passive micro remote sensing? It involves transmitting microwave signals and measuring the returned echo. It measures naturally emitted microwave radiation from the Earth's surface. It requires active illumination of the target by microwave signals. It operates only during daylight hours. So which one is correct? It measures the naturally emitted microwave radiation from the Earth's surface. This way it is different from the active sensor. It is measuring here the emittance. In active sensor, it measures the backscatter. In passive sensor, it measures the emittance. Second question, what is the primary advantage of passive micro remote sensing over optical remote sensing? So, higher spatial resolution or ability to penetrate clouds and operate in all weather, lower cost of sensors, or higher temporal resolution. Easy question. It is after all the operating in microwave region, so it has ability to penetrate clouds and operate in all weather condition. And also, but it is not operated in day night, that is the active one. So answer is B. Question 3, which physical property is most directly measured by passive microwave sensors? The reflectance, the brightness temperature, the radar cross section, and spectral absorption. So definitely we came to the term the brightness temperature. So it is the answer B. The correct answer is B, that is the brightness temperature. property is most directly measured? Obviously radar cross section is, spectral absorption, reflectance, all are there, but most directly, most correct word answer is the brightness temperature, the first. Which of the following earth observation parameter is not commonly measured using passive micro remote sensing? Not commonly measured. One is C, ice concentration, B, soil moisture, C, ocean surface winds, D, topographic elevation. So the right answer is the D, topographic elevation. It is not commonly useful or measured. C, ice concentration, soil moisture, ocean surface winds, these are the important domain of its application. Question 5. The spatial sensor microwave, that is the SSM, is a passive microradiometer system that operates at which frequency? So this operates in 6 to 37 GHz. Answer B. So important. Question 6. What is the primary limitation of passive micro remote sensing as compared to active sensing? So A, it cannot operate at night. B, cannot penetrate cloud cover. C, lower spatial resolution. D, cannot detect water content. So definitely the right answer is the lower spatial resolution. It has much lower resolution. Question 7. The brightness temperature measured by passive microwave sensors is related to which physical property of the object? Actual temperature only, emissivity only, both emissivity and physical temperature, and neither emissivity nor physical temperature. So right answer is option C is both emissivity and physical temperature. Okay. Question 8. Which of the following mission or instrument is not passive microwave sensor? This is very important. You have to get knowledge. It is expected to current ongoing mission and sensors, all those. So first one is AMSR, active microwave sensor radiometer. B, SMOS, soil moisture and ocean salinity. SMAP, soil moisture active passive radiometer, and Sentinel-1 SAR. Which one is not a passive microwave sensor? So definitely answer is D, that is the Sentinel-1. It is active sensor, but rest all are the passive sensor. Now questions 9. And the SMAP is very active passive, it has both, and SMAP data is very useful to our domain, for hydrology domain. Question 9. What is the typical spatial resolution of passive microwave sensors? Typical resolution, it ranges 0.5 to 1 meter. Obviously not, it is not that high resolution. 10 to 100 meters, several kilometers to 10 of kilometers, or 100 to 200 kilometers. So right answer is C, several kilometers to 10 of kilometers. I mean not into centimeter level, I mean not into below 1 meter, not into 10 to 100 meter, but 1 to 10 meter. Okay, not 1 to 10, I mean much more, suppose 4, 5 to 10 kilometers. The spatial resolution. Question 10. Which of the following parameters affects the penetration depth of passive microwave signal in soil? This is very important if you are interested in detection of soil moisture. Capture the soil moisture, study of soil moisture. This soil moisture content, frequency of observation, soil texture and composition, all of the above. So all of the above. Obviously penetration depth depends on the bands, depends on the soil moisture content, because the water, more the water presence, it is, it is not that much capable of penetration. Water, it performs opposite. More the dry, it can penetrate more or better. frequency of observation, soil texture, composition, all of the above. Depends on the soil also, soil particles, how much composite is, all those. Question 11. Why is passive micro remote sensing particularly valuable for flood detection in regions with frequent cloud cover? So it provides higher pixel resolution than optical sensors, definitely not. Option B, it can penetrate clouds and detect surface water beneath cloud cover. You can see it is more cost effective than other remote sensing methods. D, it provides better information about flood water depth. So option B, it is because when there is frequent cloud cover, it is operating in microwave region, so it can penetrate cloud and see through the cloud. Question 12. Which physical principle enables passive microwave sensor to distinguish between flooded and non-flooded areas? Now we come to application. So option A, the higher albedo of water surfaces. Albedo is one term. It is also it directly illustrates the dielectric properties. How much energy it can store and it can reflect. The lower emissivity of water compared to land surface in microwave frequencies, the higher thermal conductivity of water, the Doppler effect on standing water. So the right answer is option B, the lower emissivity of water compared to land surface in microwave frequencies. That is how we can, in using passive microwave sensor, we can differentiate between the water and non-water surface. Now question 13. What is a significant challenge when using passive microwave data for flood mapping in urban areas? Cloud cover interference, no, you can see through the clouds. Signal attenuation due to buildings and complex structures, we will see about it. And C, temporal resolution limitations. And D, excessive signal reflection for building materials. That we can't say what are the materials, what can be, and it is not like always reflection. So answer B, it is the correct answer, option B, signal attenuation due to buildings and complex surfaces. So attenuation in the sense how it will the signal will interact with different materials as well as the height and the shape of the buildings, the structure. So the signal can attenuate, increase or decrease. Now question 14. Which passive microwave satellite system is widely used for global flood monitoring due to its near daily coverage? This is very important to know. SMAP, the AMSR2 Advanced Microwave Semi-Radiometer 2, GPM, Global Precipitation Measurement Mission, all of the above. So these are all of the above because these all are near daily coverage. Daily it is giving you the data and open source data. Question 15. The signal of opportunity technique in passive microwave remote sensing for flood detection involves using natural variation in Earth's magnetic field, measuring reflected signals from communication satellites, repurposing active radar signals from other sources, and capturing random electromagnetic noise from urban areas. This is one out of the domain, but better to know. It is the measuring reflected signals from communication satellites. Now question 16. Which of the following flood characteristics is most difficult to determine using passive microwave data? Flood extent, flood duration, flood water depth and flood onset time. Right answer is flood water depth. Water depth is always difficult, but it depends on your band and the frequency you are using, the sensor you are using, the resolution you are using, and also based on the our target area. What is the primary advantage of using AMSR E or AMSR2 data for flood monitoring compared to optical sensor? Question 17. So it has high spatial resolution, or ability to detect smaller floods, or all weather capability and daily coverage, or direct measurement of water quality. So C is all weather capability and daily coverage. It has optical sensors. Obviously it has suppose 8 days and temporal, not daily coverage. Question 18. Which passive microwave derived product is particularly useful for detecting potential flood conditions before they occur? Soil moisture anomaly, sea surface temperature, atmospheric water vapor content, wind speed measurement. Before they occur. So soil moisture anomalies and also sea surface temperature. Soil moisture anomaly when the rainfall is happening. Question 19. The TRMM and GPM passive microwave instruments are useful for flood monitoring because they directly measure flood depth, provide near real-time precipitation data that can be used in flood prediction. C. Can see through buildings to detect urban flooding and measure river discharge rates. The right answer is B. It provides near real-time precipitation data that can be used in flood prediction. Near real-time, that means every day. And definitely no sensor can see through buildings to detect urban flooding. Question 20. Which of the following approaches improves the effectiveness of passive microwave data for flood detection? Option A is integration with optical data for validation, combining with digital elevation model to improve detection accuracy, fusion with active radar data to enhance spatial resolution, all of the above. So all of the above. Improve effectiveness. We saw the fusion with Landsat, and when you have the data, it is always better to go for fusion approach, but also there are some things to remember, that fusion of different frequency data, different resolution data, that needs very expert knowledge, expert handling of data. Otherwise you will end up with error data with much more error. So proper fusion should be done, then only you can get useful correct data. Question 21. What is the primary advantage of passive microwave remote sensing over active in terms of system complexity? So high spatial resolution, simple sensor design with lower power requirements, more effective penetration of vegetation canopy, or better signal to noise ratio. Question 11. 21 is the simple sensor design with lower power requirements. Obviously it does not need its own power, the passive sensor. Active sensor needs its own power, that is why it is much more costlier than any other passive sensors, optical or microwave. Question 22. Which is a major disadvantage of passive microwave systems compared to active systems like SARF or flood detection? Major disadvantage of passive microwave for flood detection: inability to operate at night, inability to penetrate clouds, poor spatial resolution, and higher operational cost. The first one is the inability to operate at night and penetrate clouds. So coarser spatial resolution. Inability to operate at night, I mean if you operate with you, if you take the data with radiometers, then there is no problem, but it is not getting from the sun the energy. It is working on the instrument. So but it gives you very coarser spatial resolution. Question 23. So for flood monitoring application, why might passive microwave system offer an advantage over active system? They typically have wider swath width and more frequent revisit times. They can directly measure flood depths. They provide high spatial resolution images, and they can distinguish between different types of flooding. Okay, regarding the previous question, question number 22, because it passive microwave system, it works on the emissivity, so it does not need like daytime or night time. The emission of the particle, the target during night time, still it can capture. Question 23. The right answer is, the advantage is they cover a wider surface and more frequent revisit times also, because it is not that much costly to operate a passive sensor. So the advantage lies not into the resolution, but then we can add this advantage of frequent acquisition. Question 24. Active microwave systems like SAR have an advantage over passive. Is C. Option C is ability to delineate precise flood boundaries due to higher spatial resolution. Question 25. Which of the following is the advantage of passive sensor over active? Again, it is passive sensor. The better spatial resolution, definitely not. B is the historical data availability going back several decades, as I said. So the right answer is B. The mission started a lot before, so we can get all those historical data for studies, whereas the active sensor are much more recent and not comes with the multiple bands, all those. Question 26. An advantage of active remote sensing over passive for flood mapping is, option C is better ability to distinguish flooded vegetation. Now question 27. Which of the following statements above data interpretation is correct? Passive microwave data is generally easier to interpret than active microwave data. Active microwave data requires less sophisticated algorithms than passive microwave data. Passive microwave data typically requires complex emissivity modeling for accurate flood detection. Option D is neither active nor passive microwave data requires significant preprocessing for flood mapping. So, right answer is option C. Passive microwave data technically requires complex emissivity modeling for accurate flood mapping. So, it works on, deals with the emission of the property, emission of the target. So, it needs the emissivity handling. Question 28. What is the advantage of passive sensor? Again, I am skipping this. Question 29. A significant disadvantage of passive system compared to active is higher cost of data acquisition. No. Inability to penetrate vegetation canopy and greater susceptibility to radio frequency inference in populated areas and lower temporal resolution. This is one tougher question. The right answer is correct answer is option C. It can penetrate vegetation canopy, and no, it is not higher cost of data acquisition as compared to active. Active one is higher in cost and lower temporal resolution. It is, but it has higher temporal resolution, near real time coverage it gives meaning, but greater susceptibility to radio frequency interference in populated areas. Question 30. Which of the following statements best describes the complementary use of active and passive microwave remote sensing for flood monitoring? So, the right answer is B. Passive system provides frequent wide area monitoring, while active system provides detailed flood extent mapping. So both has its own advantages and disadvantages. It depends on which we are interested. If we are interested on much more wider area, and when spatial resolution is not that much important, but when we want to look at more detail and very state level, suppose state level area, then the active sensor are useful there, because there we are getting much more smaller area, we don't need that much wide area, but we are getting high resolution of data. So for today till now, this is the this is it. I have discussed the few of the MCQ questions of today's topic, and inland water dynamics mapping, someone questioned this system is not opening. You know what the system. So I think I will see about it. I have not discussed these type of systems in my course, but I will see and I will answer in next. I think you are not in the chat now, so I will give you the answer later. For today, this is it. Thank you.